Hey, good afternoon, everybody. My name is Paul Artman from AMD.
And I'm Chris Malone from Meta.
So we're going to work together on a presentation, a kind of follow-up. We've been talking about 30°C as it being a durable temperature and kind of doing some double click on some of the details we think could be limitations going forward and why we think that's still the right direction. So it's a pretty broad effort. So in this collaboration, it includes Meta, AMD, Vertiv, Samsung, Microsoft, Intel, and NVIDIA. Actually, I have quite a good bit of NVIDIA content in this. So what we're trying to do is, as a large organization, large companies, to align on where we think we need to go in terms of liquid cooling. I know it's still premature. We're just getting into liquid cooling, but we're concerned that we want to have long-term roadmaps. So, you know, when we're talking liquid cooling, it's been around for a while. It's very, very well received in HPC. And you see a lot of reasons around sustainability, efficiency, and performance that drives that. But really what we're seeing is that GPU power is scaling significantly gen to gen, significant. It's a hockey stick, and it's getting performance gains that are significant. Where CPUs kind of flatline, so we're seeing that GPUs are going to continue to, I don't want to put a number out there, but go crazy high in power, and you know, well above 1 kilowatts, and that's driving need to do liquid cooling, and really pushing the bounds of what we can do in liquid cooling. We've been advocates of liquid cooling for myself 20 years, saying this is something that's great, but it's not infinite. So we got to be able to understand where we can go push it. So again, we're seeing GPU powers really just being a hockey stick, and we are seeing CPU powers were kind of going at a pretty high gen to gen CAGR, but they've kind of sustained, and we don't see those going anywhere near what the GPU powers are. So as we're getting into limitations on cooling, one of the things that really pops up is the package itself. So when you look at a computer, a chip, you generally look at it at a high level of two ways. One is the theta JC, that is a silicon vendor, the thermal resistant from me to the cold plate heatsink. And then you look at the cold plate to ambient, heatsink to ambient. When we were talking air cooling, initially 0.3 C per watt was a decent solution on air cooling. We're getting down to the 0.1. But what it really meant was the cooling limitation was the heatsink. It was not the packaging. Now when we're talking about 0.01 C per watt cold plates, 0.015, the packaging becomes the dominant thing. So that's one of the things we're seeing as we go forward. I've got a better chart for going forward, but just kind of showing the thermal resistances of what we tend to see is you have the ASIC resistance or GPU resistance to the lid, then you have HBM and other components, and you see also cross-heating. So what can happen is something gets hot, and it's heating the component next to it, and that limits the thermal heat transfer. And Meta did a really good example where they're showing the stacking of the HBM is actually limiting. The thermal resistance of the package is what's driving requirements. These are high power parts, but they're not nearly as high power as an ASIC, but still because of how the packaging technology is, it's becoming a limitation. And so I'll go to that in a little bit more details. What you're seeing is, again, kind of like the ASIC, the HBM power is just going gen to gen, and the stack height is getting higher. So we're seeing that as really something that is, I wouldn't say it's the dominant, but between ASIC and HBM, those are right next to each other. Which one's the limiter? You know, is it single refresh, double refresh, workload dependent, but we are seeing those being kind of very similar. And the reason that the HBM is an exploded view that actually Mark Stanky did, proved to my scribbles quite a bit on the actual resistance. But what it shows you is that stacking of the HBM, it's those multiple layers, and having to cool that lowest die to its requirements is really the limit in terms of what the thermal resistance is. So stuff we're looking at going forward is how do we improve the package? You know, we've gone from integrated heat spreader to a bare die. We're looking at higher performance TIMs. We're looking at anything around die edge thinning to get there. And then how do we actually do the other packaging around HBM, other things to improve the thermal performance? You know, and why 30C? We think that 30C is a reasonable compromise in terms of temperatures. You see a lot of deployments today at 40, 45, but those are also 200 and 400 watt CPUs. They're not 2,000 watt GPUs. In terms of, you know, we could push it to 20, but 20 has significantly more impacts on cost. So as we're doing this effort, Chris really started this effort 2 or 3 years ago. It's got very good alignment through the industry. We've also talking with ASHRAE, so we're trying to make sure that we're aligning. So within ASHRAE, we've defined very similar requirements, 30, 35, 40, 45, what we call secondary fluid temperatures. When we say 32, we want to be clear that's the bottom. If you can go 40, 45, it's great. We're all for that. But we're trying to define a bottom limit because it takes the data set a long time to develop it. And it still is, in our viewpoint, it's a really good point for efficiency. Sure, 40 degrees better, but 20 degrees is actually significantly worse. So let me transition to Chris.
Yeah, thanks, Paul. Just briefly back on this slide. So this is a great time in this industry, right? Like, as Paul said, like liquid cooling has been around as a technology forever. When I was at Google, we started implementing liquid cooling at scale back in 2018, and now it's starting to, we all see this as an inevitability. And so the next generation data center design that we started at Meta a few years ago is enabled for liquid cooling, and we expect that to be just the status quo going forward for AI machines. Right? There's still plenty of air-cooled machines in a data center, but the imperative here is to align on making liquid cooling a standard offering. And one of the things that we kind of looked at a few years ago is ASHRAE's done all kinds of excellent work for a decade plus describing these temperature ranges for the fluid. But a wide range of temperatures doesn't really help you as a data center designer. You have to pick a number when you're designing your cooling plant. And as Paul said, lower actually has some pretty severe CapEx and OpEx hits associated with it. So we have to pick carefully. And 30 is actually a really good number. It aligns well with what a lot of hyperscalers have chosen for their air-cooled machines. And that, in turn, has led to all the efficiency gains we've seen over the last 15 years, right? Like PUEs of 1.1 are old news now, right? That's kind of the status quo. So part of this is we don't want to go back and have super inefficient data centers. And so we need to pick something that kind of strikes the right balance between future-proofing and efficiency. So let me just explain a little more about why 30. This is a bit of an eye chart. This is a kind of a capture of some data that our folks on our team put together. And it's encompassed in a white paper that we published recently. And I think the link to that is at the end of the slide deck. And it's a really good study that looks at the impact of temperature, the fluid temperature, on efficiency. Essentially, like how much time are you running your chillers across a broad sweep of ASHRAE characterized ambient temperature. So it's like from hot to cold, and what does the impact look like? And in this case, it looks at using air-cooled chillers with the possibility of like trim cooling. So you do get some efficiency at lower temperatures. So it's not a worst case by any means. And it's actually kind of typical of what we're seeing these days for big data centers. Using water is really a big problem for us. So air-cooled cooling is kind of a common path these days. So this chart shows on the horizontal that range of climates from hot to cold. And we plot chiller hours over the course of a year as a function of temperatures from 20 to 40. And you can see the impact here. The chart has no numbers on it, but the impact is quite severe. And the last time we presented some results, I believe the delta between some like a 5-degree change in the coolant temperature was like a 20% hit on the chiller hours. So it's not small by any means. And so again, why is alignment important from both a server and a data center perspective? From the data center side, it takes forever to build data centers, right? We're talking about, depending on where you start counting, years to get something up and running. And then the intention is that we depreciate these assets over years, right? So most of the equipment that goes into a data center amortizes over 15 years or more. And so all the economics are built up around that assumption. The problem is if we have to change the temperature and go lower, as Paul said, high is great. Like higher, fine, just don't run your chillers. Work in econo mode more, fine. If you want to go from 30 to something lower, that means potentially some pretty substantial retrofitting and time and cost and so on and so forth. So that's challenging. Also, just like this gives us a baseline from a server perspective, from a data center perspective, of like here's the target that we should all be aiming for. And then for the silicon side, it gives us this same kind of stable foundation for like, here's what we kind of expect to go for.
I was going to comment on that because it's really helpful also is I generally have two customers. I have Google, Microsoft, Meta, Dell, whoever that is that's deploying it, and my other customer is the Silicon X guys that are doing it. And so for me, it really helps saying, you want to do 17, that's not practical. Here's an industry standard 30C, we have to figure out how to fit it. So it's a negotiation that helps across the industry so we have a common point.
That's right. Yeah, I mean, no guidelines, that tends to go poorly, right, for the server designers and eventually the data center folks. Yeah, again, there's no real specification here on how you remove the heat, immersion, cold plates, whatever your flavor. This kind of sets the baseline for what the silicon requires to operate. And we know that there's a lot of work that needs to go into chip packaging. This is an area that's incredibly challenging. It takes years to perfect at scale, major changes to how we package. But all this is needed, right? And it's also needed on the cooling side at the data center and on the server side. So a lot of innovations are going to be needed if we maintain this temperature over time. Because those of us that spend every day talking about AI see how quickly things change. So the future is a bit uncertain, so we need investments in all these areas of the stack to hold this steady. And that's not to say that there aren't going to be some products that are going to pursue something lower. But we assess based on our analysis and so on that this is the 30C temperature kind of hits the mark in terms of the mainstream hyperscaler type products. Okay, so I kind of already hinted at some of these next steps, right? So there's the one thing that is definitely new in this since our last update is we have more carefully engaged with our HBM suppliers and who are part of this group, or some are part of this group, to define a temperature spec explicitly for the HBM, since, as Paul pointed out, this is often a bottleneck for us, given the challenge of packaging this thing. So aligning the HBM product around the spec is an important step. And yeah, the other areas I already hinted at, lowering the approach temperature on the data center side buys you, a degree, or every time you get a degree of approach improvement, that translates into some pretty huge relief on the chip side. So all these things need to be pursued heavily, and packaging, as I already said. All right. And with that, we can take some questions. I think we finished a little bit early, but here's a link to the white paper I mentioned, and I believe this is like the 4th presentation.
Yeah, I think it is. I've done 3 this year, so.
So, yeah, we're excited to keep moving this thing forward. I think it's an important initiative to provide some standardization and predictability in this ever changing space.
Yeah, and what I was going to kind of add to it also is I think we're really nascent in deploying liquid cooling at scale. It's been a cottage industry for a long time with an HPC. Google's been in the forefront with this TPU, so they have probably more experience than anybody else. But as you walk across the floor, you see CDs everywhere. It is, and just to show us a good example, I think the show floor is probably 4 times bigger than last year. We had 7,000 people, and it's clear that DLC is coming. Other liquid cooling technologies also, and how do we move there fast and align on the requirements?
That's a really good point. Like, yeah, in 2021, when I gave the first talk, I don't think there was much liquid cooling on the floor. And last year, there was a lot of air-assisted cooling racks, and now I'm sure there's a lot more CDUs. So we see this kind of hitting mainstream. But yeah, to Paul's point, this is an industry that has to mature to scale to where we think things are going to be going in the very near term.
Thanks.
Any questions?
Sure.
Hello. You mentioned you guys are doing a lot of testing around thermal interface materials, TIMs. Can you talk a little bit about challenges around that and what you're seeing and what you're looking for in a good TIM?
Yeah, I think there's a lot of non-trivial stuff. Serviceability, how do you change out the TIM, especially when with these liquid loops, you're removing them and reinserting them. Aging over time is an issue. When we look at bare dies, you're looking at pretty large thicknesses in terms of multiple SoC or packaging inert. So yeah, there's a lot of things that are non-trivial. Grease has always been really good as on IHS, but it doesn't work well in this application because it moves. So, and a lot of thermal cycling too, so stuff tends to pump out. So it's just a difficult problem in terms of, I think, robustness versus performance.
Yeah, we'd love to have metallized TIMs and take the cold plate and put it right on there, but that obviously generates a lot of new considerations.
I'd love not to have a TIM at all. I'd like to, directly on the die, but that, again, how do you seal it? And there's a lot of challenges.
Yeah, we talked about the stacked memory. I think stacking everywhere is coming. So,
Yeah.
The challenge is going to keep increasing in terms of power density.
Oh, sorry.
All right, I think that's everything. Thanks, everyone.
All right. Thank you.